Hi, everyone. Thank you for joining us today to discuss caching for performance with Amazon ElastiCache and Amazon DocumentDB. My name is Cody Allen, and I'm a DocumentDB Specialist Solution Architect with AWS. And joining me today is Zach Gardner, a Senior ElastiCache Specialist SA. Zach's going to be walking us through a demo later on in this session. But we'll start off talking about what our discussion is going to be about today. We're going to dive deep into modern applications and databases, describing how the development landscape has changed to really focus on choosing the right tool for the right job, a theme that's going to come up a lot. After that, we'll jump into purpose-built databases on AWS and then go into the architecture of both Amazon ElastiCache and Amazon DocumentDB. This is going to help show how these services were purpose-built for the cloud to overcome challenges of traditional databases. I'll discuss considerations for this architecture before giving you an overview of the demonstration we're going to be showing you. Zach's going to walk us through that demonstration on how you can utilize this architecture in a real world scenario, and we'll finish off with a Q&A session. We do have chat moderators that are going to be watching for your questions, so please feel free to pop those questions into chat at any time, or you can save those questions at till the very end and we'll answer them then. But let's start off with discussing modern applications and databases. Today, developers are building highly distributed and decoupled applications. AWS is helping them build these in the cloud by using multiple AWS services to handle scale, performance, and manageability. And to understand why developers are decoupling these applications, we need to understand how we got here. Now, if we go way back, mainframes were the predominant way of building apps. The data was on the mainframe, and if we needed that data, well, we just went straight there. And this lasted until we got those client server applications. And this really changed the way applications were built. Applications started to become more distributed in nature. However, that underlying data model was predominantly structured and the database was often a monolith. Then the internet arrived and life was awesome. And as a result, we started seeing these three-tier application architectures emerging. Client and application code became even more distributed. However, that underlying data model was still predominantly structured and that database remained a monolith. Well, what's changed? Now, if you fast forward to today, the microservice architectures are how applications are built in the cloud. And microservices have finally reached the database. This is going to allow developers to do what they do best, breaking apart those large applications into smaller services and, again, pick the right tool for the right job. Developers want to avoid a single overburdened database that has a single storage engine and a single compute engine trying to handle every single access pattern. And these expectations have resulted in data management systems with specialized storage and specialized compute layers optimized for their given use case or their workload. And this is so a developer never has to trade off the functionality, performance, or scale. On top of this, what we've seen over the last few years is that more and more companies are starting to hire this technical talent in-house to take advantage of the cloud. There's this huge wave of technological innovation that the cloud is providing. And these builders are not building in those monolithic ways of the past, but with these microservices where they compose different elements together using that right tool for the right job. All of this has led to a highly distributed, loosely coupled application architecture that's powering the most demanding workloads in the cloud. The expectations for builders, as well as the end users of today's applications, is really different than the way it used to be. The latency requirements are much lower, and they're expected to be able to handle millions of transactions per second with millions of people using the app at the same time. Businesses are expanding into new localities to reach new customers, and they're capturing more data about their customers to either improve existing products or sell new products. And as we have more devices connecting, we see more and more connections hitting these applications, up to billions of devices connecting to the cloud. And because of this, businesses can't invest millions of dollars in hardware and licenses up front and hope they'll be successful. That model just isn't realistic anymore. Instead, they have to hedge their successes by only paying for what they use without capping how much they can grow. All of these dynamics combined have changed the way businesses build applications, and these modern applications have wildly different database requirements, which are way more advanced in nuances than simply running everything in a relational database. We used to throw everything in our relational databases. It could handle the reporting, it can handle the ETL. We would even throw code at our databases by running functions and stored procedures, even creating our own CLRs, common language runtimes, and DLLs to perform that. But we don't do that anymore. Again, it's that right tool for the right job. So, why are we considering purpose built databases? Put simply, we need that scale, we need that performance, and we need that availability it provides. Great thing here is AWS has purpose-built databases to meet these requirements. Thinking back to the mainframe and monolithic databases, the database landscape has changed. Much like our developers are creating microservices specific for their different flavor or code, we're starting to see different flavors of databases. No longer is relational the only category, and we have to shove the square block into the round hole, so to speak. Now we have key value stores and we have document databases. We have in-memory databases, time series, and ledger databases. Now, AWS is going to offer purpose-built database solutions for each of these types. So if you're running an on-prem RDBMS system, well, you can run that on AWS with RDS, or even move to a fully managed service like Aurora. You can take advantage of Neptune that makes it easy to build and run apps that work with highly connected data sets. But today, as you can tell by the title of this session, we're going to be focusing on these two, Amazon DocumentDB and Amazon ElastiCache. Now, Amazon DocumentDB with MongoDB compatibility is a fast, scalable, highly available, and fully managed document database service that's going to support your MongoDB workloads. The key thing here is it was designed from the ground up to give you that performance, scalability, and availability you need when operating those mission critical MongoDB workloads at scale. With DocumentDB, the storage and compute layers are completely decoupled from each other. That means that I can scale each of them independently. I can also increase read capacity to millions of requests per second by adding up to 15 low latency read replicas within minutes, regardless of the size of my data. We're implementing the Apache 2.0 open source APIs by emulating responses that a MongoDB client expects from a MongoDB server. Well, what does that mean? That means that you can use your existing MongoDB drivers and tools with DocumentDB. And by using the same tools and drivers that MongoDB provides, DocumentDB makes migration seamless with zero to minimal code changes and near zero downtime. We also have features like global clusters that allows you to build globally distributed applications that are resilient to regional failures. And as a managed service, we're removing all that undifferentiated heavy lifting. That means that you can focus on what matters for your business. And this is going to promote your innovation that's required to stay relevant today. DocumentDB is secure, it complies with various ISO and PCI DSS standards. And we have a global presence across 16 AWS regions, and we're continually adding more by listening to our customers and building what they want. DocumentDB is designed for 4 nines of availability. We're replicating 6 copies of your data across 3 AWS availability zones. And since it's all running on AWS, we get native integration with other AWS services like CloudWatch and CloudTrail, Secrets Manager, and many more. We'll dive a little bit deeper into that here in just one second. Now, Amazon ElastiCache, that's going to offer us fully managed Redis and Memcached. That means that you can seamlessly deploy, run, and scale these popular open source compatible in-memory data stores. Amazon ElastiCache for Redis, which is what we're going to be focusing on today, is a blazing fast in-memory data store that's going to give you that sub-millisecond latency to power those internet scale real-time applications. It's all built on open source Reddit and it's compatible with the Redis APIs. Well, again, what does that mean? Just like DocumentDB can use those existing MongoDB tools and drivers, ElastiCache for Redis is going to work with your Redis clients and uses the open Redis data platform to store your data. That means that your self-managed Redis applications can work seamlessly with ElastiCache without any code changes. Now you can build those data intensive apps and improve the performance of your existing apps by retrieving data from high throughput and low latency in memory data stores. Stated simply, Amazon ElastiCache is going to play a very unique role in our purpose-built data strategy, and that it's about working side by side with DocumentDB. It's really straightforward. You add a cache for that dramatic performance enhancement. Think of ElastiCache as the first responder for those application data feeds, taking a lot of pressure off DocumentDB while turbocharging its performance. Now, we do need to point out that the architecture that we're going to show you today is a very specifically designed solution. Before implementing ElastiCache in front of your DocumentDB clusters, it's very important that you understand your workloads. While having a side cache can improve your query response time, your workload and your query patterns is ultimately going to help you decide if this is the right architecture for you, because it's not going to be the right architecture in every situation. For example, if your workload includes the ability to do a lot of ad hoc queries across multiple key value pairs. So think of a customer portal where your customer can search by one or many of the key values stored within a DocumentDB document. Utilizing DocumentDB's buffer cache via direct connection from the application would be a well-architected solution. And additionally, you can continue to use DocumentDB to handle your aggregations via its rich set of supported APIs and operators. Although ElastiCache is going to send any cache miss queries to the target database, having your application connect directly to DocumentDB to retrieve the requested data can avoid unnecessary steps. And we'll talk about the different caching techniques in a second that will help illustrate that point. And since you're utilizing the buffer cache to hold your working set within DocumentDB, you still get very fast query response to your application. So ultimately, you need to decide if this is going to work for you. You need to determine, is your workload read heavy or write heavy? Today's demo is going to illustrate a workload that's read heavy, where users are performing the same query multiple times. If your workload is also incorporating heavy write traffic, adding an extra layer via ElastiCache may decrease performance by adding additional steps, ultimately slowing down that customer experience. But again, the point here is know your workload, know where this is going to improve your situation, or maybe it's not quite the right architecture. And of course, if you have any questions about that or need help, you can reach out to your AWS account team. Let's jump into the service architecture of Amazon DocumentDB to understand what it's doing behind the scenes. Now, since your applications can leverage the same MongoDB drivers you currently use, that also means you take advantage of connection parameters like read preference. In this first example, we're going to see what it looks like when your application uses a read preference of primary for those read after write strong consistency results. Now, our best practice when using DocumentDB is to use a secondary preferred read preference. And that's so that your primary can focus on doing all the writes, while those replicas can do the heavy lifting of reads. But you are able to connect however your application needs by specifying that read preference. So here we can see our applications doing a simple find operator against our collection to find this one document. Well, when the documents that your application needs are located within the working set in the buffer cache, they're going to be served from memory. DocumentDB is going to return those documents immediately from the compute layer, and it never has to reach into that distributed storage volume. Well, now let's talk about our preferred method of using secondary preferred for that read preference. Again, this is going to send all those reads to the read instances and only send reads to the primary if all the other replicas are unavailable. This is going to really open up that primary to just handle those writes and be extremely performant. We have the same situation here. The documents are in the working set of that replica, so there's no reaching into that distributed storage volume. It's returned immediately to that application layer. But what happens when our find filter changes and now we need a document that isn't in memory? Well, the compute instance now has to reach back to that disk and retrieve the requested document. This is also what happens when you perform a collection scan against DocumentDB due to a missing or inefficient index. If it cannot find the answer, if it cannot find that document in memory, it's going to have to reach back into that storage layer. Now, DocumentDB is using a read quorum of 3 on that storage volume. And this is part of our high availability default architecture that gives you those 6 copies of your data across 3 availability zones. So even if an entire availability zone was lost in the storage layer, you'd still have enough copies of your data to continue reading while that AZ is recovered in the background. So here, the storage instance or the storage layer is returning those docs back to the compute instance. The important thing to point out here is that one of the dimensions for pricing with DocumentDB is IO operations. So every time that your compute layer has to reach into storage, there's going to be a charge associated to that. An IO read operation is 8 kilobytes, and an IO write operation is 4 kilobytes. So again, if we don't fit the documents that we need within our replica, within the working set, there's going to be a cost to that, both with performance, because reading from disk is slower than reading from memory, and through a billing mechanism for those IO operations. Finally, our compute instance has that data, and it can return that document back to the client. Now let's switch gears and talk about the service architecture for Amazon ElastiCache. Now, when you're building a distributed application, we want to achieve that low latency and scalability. We've already seen how DocumentDB solves these requirements by utilizing instance memory, that buffer cache for your working set, and adding up to 15 replicas to help scale reads. ElastiCache is going to take that concept further by giving you that blazing fast in-memory data store with that sub-millisecond latency. We'll walk through specifics on how to implement this architecture here in a second, but from a high level, your applications are going to leverage ElastiCache to access the data in a particular structure or view to simplify that data retrieval and increase application performance. Now, depending on your workload, this can also help with cost, as we can scale ElastiCache to handle those extremely high repetitive reads instead of scaling out DocumentDB with more replicas. We'll double click on that here in just 1 second. And you're also going to get that optimized key value index lookups based on that in-memory microsecond latency. Now, the first caching method that we'll look through with ElastiCache is write-through caching. Here, data inserts or updates are written to both the cache and the database. The advantage here is that because the data in the cache is updated every time it's written to the database, the data in the cache is always current. There will be a penalty though, a write penalty versus a read penalty, because every write involves 2 trips. We have to write that data to the cache, and we also have to write it to the database, and that's going to add some latency to the process. But end users are generally more tolerant of latency when updating data than when reading or retrieving data. There's this inherent sense that an update is more work and it's going to take longer because of that. Now, the disadvantage here is if you spin up a new node, whether it's due to a node failure or you're scaling out, there's going to be missing data. And that data is going to continue to be missing until it's added or updated on the database. Now, you can minimize this by implementing architectures that put lazy loading with write through, and we'll talk about lazy loading here in just 1 second. But just understand that you will have to redesign your architecture based on those requirements. Now, there's also cache churn. And what I mean by that is most data is never read, which could be a waste of resources. Since you're always writing it no matter what, it's not guaranteed that it's always going to be read. Now, in today's demo, we'll focus on lazy loading or read-through caching. And in this process, we're doing 3 different things. The first thing is the application is going to check the cache for results. And if it has a cache hit, then ElastiCache is going to return that result back. However, if there's a cache miss and ElastiCache does not have that information, the application is going to go to the source to get it, and then ultimately update ElastiCache with that new data. Now, the advantage here is because most of the data is never requested, lazy loading can avoid that situation we just talked about, where we're filling up the cache with data that isn't needed. And if a node fails and is replaced by a new empty node, your application is going to continue to function, although there will be some increased latency there, because as requests are made to the new node, each cache miss results in a query of the database. And at the same time, the data copy is added to the cache so that those subsequent requests are retrieved from the cache. Now, the disadvantage here is if there is a cache miss penalty. Each cache miss results in 3 trips. We have to do an initial request for the data from the cache. Then we have to request the data from the database because it's not in the cache. And then we have to update the cache for those new results. And these misses can cause a noticeable delay in data getting back to the application. Additionally, if the data is only written to the cache when there is a cache miss, that means the data in the cache can become stale. And we'll talk about techniques to deal with that here in just 1 second. And this is occurring because there's no updates to the cache when data is changed, inserted, or updated, like we talked about with the write-through caching. So just a brief comparison of the two strategies. Lazy loading is going to be that read-through, where write-through is going to be on inserts and updates. There are cache miss penalties on lazy loading because we have to do those 3 trips if it's not there, whereas the write latency is always putting those new inserts and updates into cache. And because of that, the data is never stale with write through, whereas data can get stale with that lazy loading. Let's talk about considerations. Why would I do this? Where does this make sense, and what kind of workloads and architectures will I do this for? Well, from a compute layer, we can leverage ElastiCache to reduce the number of connections to DocumentDB. Now, DocumentDB has limits and quotas around the number of cursors and connections it can handle on the instance level. For example, at the time of this recording, uh, our R524XL instances can handle up to 30,000 connections per instance. It's a lot, right? But if you think about an event where a situation where you have an auto scaling event, you're probably adding more EC2 instances. You're adding more containers. You're adding more resources to EKS and ECS. More containers to handle more customer connections that are reaching back to your DocumentDB cluster. Now, there are going to be some situations where you might be using a driver that's not using connection pooling efficiently. It's not using existing connections, it's opening up new ones, or you haven't capped the number of connections a connection pool can make on that container. And in those kind of situations, especially during a huge auto scaling event, you can run out of connections very, very quickly. But with ElastiCache in front, you can offload those queries covered in the cache to the caching layer without ever connecting to DocumentDB. So that means based on your workloads, because you have fewer connections and queries hitting your compute layer, there might be an opportunity to resize your instances to a smaller instance type. And I'll double click on that here in just 1 second. When we talk about network, we focus on the time it takes to get our application the document it needs to fulfill the query. By leveraging ElastiCache in front of DocumentDB, you get that sub-millisecond latency. And you also can leverage those Redis clusters with replication to distribute the workload. You're also going to get cache control with ElastiCache. You only cache the subset of data that you need. So instead of caching the entire document, ElastiCache gives you the ability to fine-tune the data that's being returned. So if you have a subset of hot data, such as content that's suddenly really popular, you can improve your customer experience by only returning that smaller subset of data quicker than you would return a larger data set. The name Redis actually means remote dictionary server, and a dictionary is a general purpose data structure for storing a group of objects. As you can see, Redis supports a full range of data structures. At the very bottom here, we have bitmaps and bitfields. And for today's demo, at the very top, we're going to be focusing on strings. But this again focuses on the need to understand your data characteristics and what's important to return to your customers. Redis is going to help with those known repetitive query patterns for desired key value pairs. It's up to you to define upfront what the important or hotkeys are in your document DB collections so that ElastiCache can return those. The other added benefit, though, is that you can control should be returned and even what can be removed from cache. So although you need to be sure and define upfront what keys are important to return, you also have the granularity to control what's in the cache and what can be removed. Finally, from a cost perspective, you could potentially decrease your IO operations in DocumentDB by serving these repetitive and similar queries from the caching layer. I'll give you an example. Let's say that you have Profiler enabled on your DocumentDB cluster, and Profiler is going to store any long-running queries into CloudWatch. So you can review those. You can see what the query was and what the execution plan and where it was doing an index scan versus a collection scan. And let's say that you've identified a slow running query that's doing a collection scan. Now remember, when we were talking about the architecture of DocumentDB earlier, a collection scan is going to hit disk. It is not going to be served by the compute layer. It has to reach into disk, which means I/O operations. Well, ElastiCache can help in this situation by serving the results of that collection scan query up front while you focus on creating your index on DocumentDB, avoiding repetitive collection scans. So instead of all these applications hitting hundreds, thousands of times even, all doing this repetitive collection scan using IOs, ElastiCache can offload that and serve it through the cache. And like I mentioned earlier, less connections and less resource consumption on your DocumentDB cluster can change your architecture size requirements. You could potentially scale down your instances from maybe an R5 4XL to an R5 2XL. And you might even be able to scale down the number of instances that your DocumentDB cluster is using. Additionally, both DocumentDB and ElastiCache allow you to go global. Now, with DocumentDB, you can leverage the recently released global clusters to help with disaster recovery and even data locality. Since the data is replicated in near real time, global clusters allow you to be up and running in a new region in less than a minute if a regional outage occurs. And since that replication is offloaded to the storage layer, there's going to be little to no impact to your application performance since the application's connecting to the compute layer up front. So that means that you can leverage those low replica lags of less than 1 second to even utilize those secondary clusters to perform local reads, letting you build that globally distributed application. Similarly, with global data store from ElastiCache, you can create cross-region read replica clusters that give you the low latency reads and disaster recovery across AWS regions. When you create a global data store in ElastiCache, it's going to automatically replicate your data from the primary cluster to the secondary cluster. ElastiCache then sets up and manages that automatic asynchronous replication of the data between the two of them. A global data store can help increase the responsiveness of your application by serving those low latency geolocal reads across AWS regions. And by pairing these two services together, we can further improve that customer experience by globally reducing latency to access data. Additionally, if you needed to expand to a new region where maybe DocumentDB wasn't yet available, you could leverage global data stores from ElastiCache to serve up hot data in a region where your customers are and that it is available. Now, both ElastiCache and DocumentDB give you integration with other managed AWS services that can help you achieve those security, compliance, or administration needs. CloudWatch is going to give you the ability to see what's going on in your clusters. Things like CPU usage, freeable memory, network allocation. Specific to ElastiCache, you have a simplified way of seeing cache hits and cache misses. And with DocumentDB, you can see things like your read IOPS and write IOPS. In both cases, you get to monitor replication lag in your cluster and total number of connections. I already mentioned with DocumentDB the ability to enable Profiler to view those slow running queries, but you can also enable auditing, which lets you see those DDL events. And from there, you can create your own metrics to watch and learn on. For example, if you want to see when you have a high number of failed logins or anytime somebody's created a database, you have the ability to do that through CloudWatch. And all AWS services utilize CloudTrail. This is something you can't disable. So any API calls made to these services, whether by SDK, CLI, or console, those are going to be tracked here. Additionally, both ElastiCache and DocumentDB can leverage Secrets Manager to safely store database credentials instead of embedding those into the application, either through an environment variable or through a local config file. Previously, if you were going to rotate your credentials, you had to invest time and update each one of your applications with those new credentials. After you did that, you would go distribute your updated application. And if you had multiple applications that were sharing those credentials and you missed updating one of them, the application failed and you had to start over again. And because of that risk, many customers choose not to regularly rotate those credentials, which is effectively substituting one risk for another. You don't want to do that. But with Secrets Manager, you utilize IAM policies that control access to DocumentDB and ElastiCache and allows your applications to connect. Lambda is going to allow us to run that serverless code, and it plays a lot of parts in integrating these databases with other services. So for example, Lambda can run as an action to a CloudWatch alert, such as adding another DocumentDB instance to our cluster when we see active connection spike, or we know that we could use another replica. Lambda can go do that for us. Or Lambda can even scale out our Redis cluster to add more shards. It can take care of these expansion jobs that we need. Lambda is also going to be utilized by secrets managers to do those credential auto rotations we talked about, either on a preset schedule or on demand. And finally, the most obvious one, Lambda can run our application code for us without the need for instances at all. Using those IAM roles and policies, we can give our Lambda code the limited access it needs to reach to ElastiCache and those DocumentDB clusters. Let's shift over and talk about today's architecture, what Zach's going to be showing us. Now, in today's demo, we're going to be looking at an application that allows users to search a movie database for different key value pairs. Zach's going to show how a user could search for a movie by its creation year, for example, through a REST API client to the application engine. That application engine is going to process that API request and retrieve the JSON document that holds the movie details from the ElastiCache layer. If there's been a prior request for that movie, well, that's going to be served by ElastiCache. If not, the application engine is going to query DocumentDB and return that requested document back to the application again as a JSON document. Then the application will cache a copy in ElastiCache to speed up the response time of any subsequent request for the same movie. The demo will be using that caching technique we talked about earlier, lazy loading or read-through caching. It's going to illustrate how ElastiCache and DocumentDB perform together for different query complexities. We'll start off looking at a relatively simple query. This query is actually doing an index scan on DocumentDB because it's covered by the index. It fits in working set. It can be served out of the buffer cache. But what we're doing here is giving you an example of how ElastiCache can help if there's a huge burst of clients all requesting similar data returned by this very simple query. Next, we'll increase the complexity. We'll query on multiple fields, one that's indexed and one that's not. Again, these can be handled by DocumentDB, but ElastiCache is helping some of the more intensive execution plans. Remember that ElastiCache is not actually performing the logic that DocumentDB cluster is. Instead, it's matching on those similar queries to return the results. That means that even with ElastiCache in front of DocumentDB, you can still reach back to DocumentDB and do those ad hoc queries that you need. Finally, we'll increase the complexity by performing a regex lookup against an index field. DocumentDB, just like before, is going to utilize an index for this search because we're passing along that hint operator. In each of these scenarios, we'll be able to see where we have cache hits that ElastiCache is handling and cache misses that go directly to DocumentDB. And what's really cool about this, the thing that gets me most excited about it, is Zach's going to show us what that customer experience is like. We get to see the response time for both those cache hits and misses to truly understand and appreciate that sub-millisecond latency. I will hand it over to Zach now to start walking us through our demo.
Thank you so much, Cody, and thank you all for joining us during this webinar. As mentioned, my name is Zach. I work with the Amazon ElastiCache specialist team here at AWS, and I'm excited to present a demonstration which speaks to the value of introducing caching, specifically on Amazon ElastiCache for Redis, into your architecture. So we'll look at a few examples. Thank you, Cody, for looking through some of the queries that we're going to model as part of our interactions between Amazon DocumentDB and Amazon ElastiCache. And I've built a small test harness, which is responsible for making a series of calls to the two databases, data stores, in order to support that caching use case. So let's transition over there. Here we can see just a brief demo application, as I mentioned, that is built in order to proxy calls between DocumentDB and Amazon ElastiCache. And when setting up a caching strategy, it's important to understand what are the dimensions of your data in order to benefit from having calls to a cache. Right? There might be situations where the data changes so frequently that the overhead of introducing a cache isn't worthwhile. But there are definitely other situations where you're repeatedly reading a series of information that can drastically be improved in terms of latency, as well as to offload resources and calls to your primary data store. So in our example, we have Amazon ElastiCache as that in-memory low latency layer in front of Amazon DocumentDB, while allowing DocumentDB to focus on the value-added work such as processing the queries and retrieving data in a variety of forms and fashions. So as we look at some of the dimensions to consider in our caching strategy, the first is a cache TTL. So we talked about cache churn, for instance, and how if I write something to the cache, there's a good chance that I'm going to want to retrieve it in order to gain some of those performance benefits. Now, when I'm speaking with customers and they say, well, the TTL of the data is only 1 second or 2 seconds, meaning once I retrieve it from the data store, DocumentDB in this case, I only want it to live there for 1 or 2 seconds, and the likelihood that I'm going to call that information is relatively low. Now, of course, understanding the dynamics and characteristics of your data, it will start to inform which data access patterns repeatedly serve relatively static information and would benefit from that caching layer. So for our use case here, we'll set a cache TTL, meaning time to live, for about 30 seconds. The next dimension is how much data do I really want to store in my cache at any given time? And on Amazon ElastiCache for Redis, we can support upwards of over 300 terabytes of data of in-memory storage in your cache if need be. But here it's helping us maintain a ratio between the number of different queries we want to call and the total number of calls. So think of this as a ratio in terms of how variable are the different queries that are being called. If I need to store 1,000 different queries at a time, I need to store 5,000 different queries at a time, that will impact the amount of in-memory storage I need on Amazon ElastiCache. So as mentioned, we can scale to reach extremely high volumes of data, but for our use case here today, we'll settle on maybe 400 different queries. And finally, as you look at the request rate, so as I put items in my cache, let's say we want to keep them there for 30 seconds or definitely longer, we've seen that. How frequently am I actually calling for that information as to achieve some of the benefits of cache modeled by this metric here, cache hit ratio, meaning how often did I find an item in the cache already and return that back with that microsecond latency and avoided the call to DocumentDB. So here we have 5,000 total calls, which will be considered as part of our caching strategy. And next, as Cody alluded to, there's different complexity as it relates to what actually gets executed on the source system, in our case, DocumentDB. As mentioned, we had a low query complexity, which was running a simple lookup against an index. We will have a medium complexity query, which will actually look at an indexed field, but then perform further validation or further filtering. And finally, we have a high complexity query, which would perform a bit more loosely structured analysis, such as through a regex. So we can run different queries against the system of record and understand what the impact would be. So I'll run my first use case here, and we see the cache is kind of warming up, right? And we have a cache hit ratio against relatively low complexity queries, putting us around 90% cache hit ratio, meaning this was the time we looked for an item in the cache. If it wasn't there, we wrote it to the cache. And then on repeat requests, we actually were able to serve it in the cache because it wasn't evicted, right? So we chose to store the item for 30 seconds. Now, when we look at some of the performance benefits attained, now keep in mind, this is not a performance benchmark of ElastiCache. This is not a performance benchmark of DocumentDB, merely just a point of reference of how a single application can sequentially call these resources in order to benefit from the two different calls out to ElastiCache and DocumentDB. So just by a cursory understanding of how to make those calls, we can see around 3,000 commands per second or requests per second going to ElastiCache and around 451 requests being served from DocumentDB. And now we'll run it again, but this time we'll run a bit more complex of a query. So we'll run a high complexity query, meaning the database has to perform more work, which means that the ratio between the commands per second and the database queries per second will definitely change. So we start it up again and we see that ElastiCache is serving the data with that consistent throughput because the data is already pre-calculated. It is ready to be served up from the cache. And DocumentDB has to perform, of course, a little bit more work to process that more complex query. So in this case, it's running a regex operation. So here we see about 77 database queries per second compared to about 2,300 on Amazon ElastiCache. Now I wanted to just transition over into Redis so that we can see an example of how this might look from a data perspective. So I'll run my console so I don't let the data expire on me, and I'll transition to my command line. So here I have Redis. I'll just log into my host. And I want the Redis CLI. And that is running on Amazon ElastiCache, which is behind this environment variable, my Flask Redis host. So we can see that I'm connected to ElastiCache. The next thing I can do is run the keys command. And here you can see some final keys, which have not yet been evicted, but I'll run my console quickly here again so we can see what happens in the cache. So we run that, and I'll run my keys command just for everyone at home. Don't run this in production. It's a blocking command for the server. But we see examples of keys now in my database. If I run db size, we can see there are about 406 keys in the application in Redis. So we'll just run this one more time, this time with some low complexity queries, and we'll actually look at some of the keys. So you can see I've modeled my data using the complexity as part of the key prefix. And this is generally a best practice to understand what type of information is in the cache before you have to access a key. So I run one example, I see a movie returned. I run another example, I get a different movie returned. And these are hopefully showing you exactly how data can be modeled, at least in a primitive sense, using the string data type within Redis. There are a variety of other data structures which can be used to model different access patterns, especially if you need to maintain a sorted order of key value pairs in memory. There's a sorted set data structure. There are sets and lists to be able to represent different result set objects in a more native way on Redis. For this example, we just looked at a simple key value pair modeled based off of, as you can see here, the concatenated version of the type of query I've run. But at the end of the day, it really just depends on your data access patterns and whether or not you could even further specialize by taking advantage of some of the Redis data structures available, purpose-built for a variety of different internet-enabled use cases. So with that, I'll transition back from the demo, and certainly want to thank you all for being a part of this presentation. It was really great getting a chance to do a webinar alongside Cody and the DocumentDB team. As mentioned, if you have any questions around DocumentDB or Amazon ElastiCache, we'll be happy to stand by and answer them after this session. And thank you again for attending, and we'll speak soon. Thanks.